Hi, I'm Kenjin. I'm the leader and my part is to design the whole program flow and the block diagram. This is the block diagram I did to show the flow on how signal is transmitted and received with several functions, which will be talked about later by my member. The highlighted start nibble is assigned in the project manual, which is 1010, and the end format block diagram is the encoded receive signal.
My name is Loichi and my matrix number is 225724 and I will be presenting the XOR checksum generation for the system. At the transmitter side, the transmitter data nibble is 1010 and XOR operation is performed on all bits of the data, resulting in a checksum value of 0. This value is then stored as the expected checksum, which will be used as a reference for error detection at the receiver side. At the receiver side, the same XOR operation is carried out on the decoded data bits after Manchester decoding. The receiver then recalculates the checksum based on the received data. The receiver compares this recalculated checksum with the expected checksum value that was generated at the transmitter. If the checksum value do not match, it indicates that an error has occurred during transmission. In this case, the checksum check is considered failed and the red LED will light up to signal the detection of an error.
Hello, my name is Neo Yong Ling. I will explain the Manchester coding logic. So it is used between the checksum generation and BFSK transmission stage. Its main purpose is to improve data reliability by ensuring that every data bit contains a signal transition, making synchronization easier between the transmitter and receiver. In this project, each binary bit is converted into Manchester code pair, where bit 1 become 10 and bit 0 become 01.
Hi, my name is Xin Ziyu. My matrix number is 225049. I am responsible as the bandpass modulation engineer, which focuses on the BFSK logic. First, the input digital data is shown as the pulse modulation waveform after the Manchester coding. Then my part will convert this pulse signal into a BFSK signal waveform. In this BFSK, the bit 0 is represented by the lower frequency while the bit 1 is represented by a higher frequency. The ESP32 generates these different frequency pulses based on the coded bits. At the receiver side, the pulse timing is measured to detect frequency and decode the receiver bits. To show how the digital data is transmitted using the frequency change in bandpass modulation.
My name is Ong Yishuan. The metric number is 225230. To evaluate the system overall robustness, a stress test was performed, especially on the synchronization module under challenging conditions.
So now we conduct a jitter stress test on our synchronization module to determine its exact operational limit. So at first, at the 0 microseconds, the status will always be passed. So when we add the noise, around 150 microseconds, the status also always is passed. So when the noise is added until 250 something, the status will become pass or fail. It's because that the module is enter a highly sensitive boundary range where performance become marginal or prone to intermittent failure. After that, when the status is become 300 microseconds, the status will become fail. It's because that the synchronization break up entirely. This gives us a clear picture of our system tolerance threshold under high noise environments.